Record. Okay. Now we're recording. So today we're going to start chapter 1 information. We're going to talk about properties of life. We're starting on basically page 18 of your textbook if you like to follow along. So what do we mean by properties of life? Well, last time we met, somebody correctly stated that the word biology, this literally means the study of life, because the word bios is the Greek word for life. So biology, it's a science because of the way information is gathered, but it is literally the study of life. So you'll find that scientists like to define everything. They like to describe everything in incredible detail. And one of the things that we like to describe is, what does it mean to be alive? What are some signs of life? Or what does it mean to be alive? And there's some general properties or some signs of living things that are common to everything that is considered to be alive. And one of the first signs of life, and I may go out of order than what's in your textbook, but one of the first things that's considered to be a sign of living things is that living things are made of cells. Living things are made of cells. They can either be one cell big, which is unicellular, or they can be more than one cell big, which is multicellular. But all living things are made up of at least one cell. So some things are one cell big and one cell big only. Others are more than one cell big. Examples of things that are unicellular, things like bacteria. All bacteria are one cell big. Yeast are also one cell big. Another example, some algae, some protists are one cell big. Things that are more than one cell big, oh my gosh, you could probably go on and on, but pretty much all plants. I think there is a unicellular plant, but most plants, animals, a lot of your fungi, although some of them are one cell big, and a lot of protists can also be multicellular. There are some statements that all living things kind of adhere to, what's called the cell theory. And the cell theory kind of relates back to this idea that all living things are made of cells. So the 3 statements of the cell theory, which you should know for the chapter 1 quiz, they're not listed in chapter 1. So make sure you write this down, or at least that you revisit our video or revisit the notes that I post later. I'm going to put a star by it because for sure this is going to be on the quiz. But what are the 3 statements of the cell theory? The first statement is all living things are made of cells. And it sounds a lot like what we've already stated, and it is. The second thing is kind of like the cell is the basic unit of life. And what this statement actually means is nothing smaller than a cell is considered to be alive. So the smallest possible living thing is a cell. Cells are made up of other parts, but those other parts are not considered to be alive. They have elements of living things, but they themselves are not considered to be alive. So the smallest living thing that we recognize as a living thing all by itself is a cell. And the last statement says cells come from pre-existing cells. So in other words, all cells, they come into existence from other cells that are already present. This last statement does not answer the question, where did the first cell come from? That's another discussion, that's another lecture. So we're not saying where did the first cell come from. We're saying is the cells that we see today, where'd they come from? Well, from other pre-existing cells. So you have basically one cell can divide and you create two new cells. Where did these guys come from? Well, from a pre-existing cell. So the first sign of life, or the first property of life, or sometimes these are called the characteristics of living things. Depending on where you look, sometimes if you go online, you'll see characteristics of living things or properties of life. But the first one is that all living things are going to be made of cells. The second property of life second characteristic of living things is that cells use DNA as their genetic material. So living things, and I'm just writing cells in place of living things, but they use as their genetic material DNA. And you guys are sophisticated students. You probably know that the word DNA, it's actually an abbreviation for this really long term. Deoxyribonucleic acid. My students these days are much more sophisticated than the students I had even 5 years ago, and they've all heard of DNA. They all understand this idea of DNA. But all living things use DNA as genetic material. What that means is genetic material, this is the stuff in a sense, and I wish I had a better word than stuff. Maybe I'll say substance, although the word stuff is easier to spell, but is the substance of heritability. It's the stuff or the substance that gets passed on from one generation to the next. And so if you think about yourself, you did not inherit your actual muscle tissue from your parents. You built your own. You did not inherit your actual skin from your parents. You built your own. You didn't even inherit your very blood from your parents. You built your own. But how did you build your own skin, your own muscles, your own blood? How did you do that? Well, you had to have information on how to build things. And that information is the genetic material. In other words, when you came into existence, you actually came into existence with a set of instructions. And those instructions were not created out of thin air. Those instructions were inherited. They were inherited. So in case you need a quick biology lesson of how you came into existence, here's the egg cell from the mom. Here's the sperm cell from the dad. And both the egg and the sperm, they contain their own set of DNA. So both the egg and the sperm contain their own set of DNA. When the egg and the sperm fuse together through fertilization, you have this new cell called a zygote, and it's inherited DNA from the egg, and then it inherited DNA from the sperm. But all of that DNA now belongs to the zygote. That DNA is literally a set of instructions on how to build whatever you need in order to be the thing that you are. So again, you did not inherit your actual blood from your parents. In this egg and this sperm, there's no blood inside of there. There's no muscle inside of there. There's no skin cells, nothing like that. Instead, all that you really inherit from your parents is a set of instructions so that you can build your own stuff. That's what we mean by heritability, the things that actually gets passed on from one generation to the next. And it turns out there's only one substance that living things use as genetic material, and that's good old DNA. Now, there are other non-living entities, and there are some interesting things that use an alternate to DNA as genetic material. So I'm going to put on here, not so much an exception, but just so you know, because you might see this on a quiz, there is a substance called RNA, which equals ribonucleic acid, that is very similar, but not exactly the same thing as DNA. It's in the same chemical family as DNA. But there are some entities that instead of using DNA as their heritable material, they use RNA as their genetic information. And a good example is viruses. We're going to be mentioning viruses quite a bit today, and we'll talk about them even some more on Wednesday. But viruses, they are not considered to be living things. They are not living things. One of the reasons that viruses are not living things is they are not made of cells. And number two, some use RNA as genetic material. So right off the bat, virus, of course, we are surrounded with the word virus because of the current pandemic. But even before then, if you play video games, it seems like almost every video game, there's some sort of crazy virus that has infected the people in your video game and turns them into crazy zombies. My husband is a gamer, so I watch a lot of video games. I play video games, but I don't play the same ones that my husband plays. I like games like Tetris or puzzle solving games. My husband likes RPGs. I don't know if any of you are gamers. Any gamers out there? Just curious. Type in a number 1 if you're a gamer.
Nerd.
Brandon, I knew you were a gamer.
I'm a gamer.
You're a gamer also? What games do y'all play?
Modern Warfare.
Modern Warfare. Oh, have you ever played or heard of, oh my gosh. Oh, I'm going blank, but the character's name is Solid Snake and Liquid Snake. What is the name of that game? Snake is on there. My husband played Halo there for a while, but I've heard of Modern Warfare. I have not seen Modern Warfare, but I've heard of it.
Yeah, that one, Modern Warfare, is pretty good.
Is it a good one? My husband likes games like The Last of Us. He just finished that one. Have you played that?
My brother has. That's a hard game for me. I don't like puzzle games.
Yeah, that's I'm only bringing that one up because it's all about like being infected by a crazy virus.
Yeah, but it's a cool game though. It's a pretty nice story.
It is. When certain things happen to one of the characters, my husband was mad for like a day and a half. And I'm like, what happens when, I have terrible things happen in my life? Do you care as much? And he's like, oh yeah, I totally care. But Ellie, on the other hand, but no, my husband, I'm trying to think of the name of the game that he's playing right now. He's almost finished. I'm gonna have to ask him, but it's the same thing. There's a crazy virus and everybody's infected. And anyway, when I talk about viruses, the first thing I think of is my husband's video games, not COVID-19, even though that's everywhere too. But just so you know, even though I'm going to talk about viruses as examples, they're going to be non-examples. Okay, a virus is a non-example of a living thing. And so one of the reasons that it's a non-example is because not all of them use DNA as their genetic information. Some of them do, some of them don't. But viruses are not made of cells. They're not made of cells. All right, so moving on. Another characteristic of living things, besides being made of cells, besides using DNA as their genetic information, is that living things, they display what we call a hierarchy. Sometimes we say that they display a level of organization. Okay. There's some organization about them, or they belong to a hierarchy. And here's what we mean by living things are organized. A lot of times they have smaller parts. Okay, they have smaller parts. The smaller parts themselves are not necessarily alive, but they constitute a living thing. Okay, so smaller parts that are not alive by themselves, but instead work together to constitute a living thing or to make up a living thing. And I'll give you an example. A while ago, we said that the smallest living thing that can exist is a cell. So we'll start here with a cell. That's the smallest living thing that can exist. Well, a cell itself is made up of smaller parts called organelles, literally little organs. Okay. Now, organelles are not alive, but together they can help make up a cell. And so some examples of an organelle, if you've had biology before, these words might sound familiar to you. The nucleus of a cell is kind of like the brain of a cell. My favorite is the mitochondria. Yes, I have a favorite organelle. Who doesn't? My other favorite, it's kind of like 1A and 1B, I guess. They're both my favorite, is the chloroplast. These are structures that they themselves are not living by themselves. However, the nucleus and the mitochondria, the chloroplast, plus a bunch of others, they all work together in order to make up a cell. Organelles themselves are made up of smaller parts. They're made up of what we call organic molecules. So we have organelles, we have organic molecules. And you've heard of these different organic molecules, like you guys have probably heard about carbohydrates. You've probably heard the term protein. You've heard the word lipids, which is a fancy word for fats, basically. And the other category, nucleic acids. So there are 4 types of organic molecules that make up organelles. And so all organelles are some combination of proteins, carbs, lipids, and nucleic acids. They themselves are made up of atoms and elements. And so some example of atoms and elements, you won't be surprised to hear that a lot of living things contain carbon. A lot of living things contain oxygen, hydrogen, nitrogen, etc., etc. So this is what we mean by an organization or a hierarchy, is that even though the cell is the smallest living thing, it itself is made up of smaller parts. These things are not alive, but together they can constitute a living thing. Now, a cell is the smallest living thing, but it itself can contribute to make larger living things. So for example, you can get a bunch of cells that work together for a common function. We call them tissues. So this is a group of cells with a common function. And so examples of tissues, if we're talking about humans or animals, might be like connective tissue, or maybe even muscle tissue. If we're talking about plants, there is a type of tissue called parenchyma. I'll put plants there. That way you don't think that, people have parenchyma. We don't have parenchyma. That's a plant tissue. If you eat celery, the kind of the white stuff inside of celery, not the strings, but the other stuff that's not strings, the white puffy stuff, that's parenchyma. That's a good example of where you can find it. Of course, you can get a group of tissues that work for a common function. Oh, I'm running out of room here, but they make up an organ. And then a group of organs make up an organ system. And then an organ system can make up, or 2 or more organ systems make up an organism. There we go. I'm running out of room on my paper, but an organism. And I'm going to put a box around organism. Now, what is different between cell and organism is that tissues are alive, organs are alive, organ systems are alive, but these do not live very well on their own. We can have tissues, like we can grow skin tissue, or we can grow, we're trying to grow entire organs in the lab, but they need a lot of support. They don't grow very well on their own. We have to really, really nourish them, support them, keep them in the right temperature. We have to bathe them with the proper nutrients and liquids. It's hard to keep a heart alive outside of the body. However, it is considered to be living because it's made up of many, many cells, but it doesn't live very well outside of the body on its own. The reason is because when we get to tissues, organs, and systems, is these are specialized cells. These are made of specialized cells. And when cells are highly specialized, they are highly interdependent. So cells that are very specialized, they are interdependent on other types of cells. So for example, a cell that constitutes the heart is specialized from cells that constitute the brain. In fact, when we look at brain cells, we actually have brain cells that are so specialized that they can only do certain things on their own. They have to have other cells help them with really what we would consider to be like daily activities of living. There are some brain cells that are so specialized that they don't even bother to feed themselves or get rid of their own waste. And so we have other types of brain cells that are specialized to protect those cells that have somehow lost the ability to efficiently feed themselves and efficiently get rid of their own waste. They're that specialized. And so when we look at specialized cells, they have learned to do 1, 2, maybe 3 things so well that they have minimized or lost their ability to do other things for themselves. So they depend on other cells to help them maintain their ability to stay alive. That's why all of these specialized systems help constitute an organism. Remember those words unicellular? Unicellular organisms kind of stop right here, but this is a multicellular organism, multicellular. And so unicellular organisms will not exhibit tissues. They won't do that. They won't exhibit tissues. But they will, depending on the organism, they might kind of take an alternate route and create what's called a biofilm. And a biofilm is a group of unicellular organisms that almost act like a single organism. They live in a large colony. And they can, to some degree, behave or act like a large multicellular organism. So a good example of a biofilm might be something like pond scum. You can have, if you remember from the video that we watched, the tetrahymena, which is the organism that Elizabeth Blackburn very first studied. Tetrahymena is one cell big, but it can form a layer on top of a body of water. And those individual cells, they begin to kind of make connections one to another. And then they begin to almost form what is almost like a large skin, which acts like a single organism on top of the surface of the water. So they can colonize and almost behave like a single organism. The difference between a biofilm and taking like, a piece of an organism is that if you remove parts of the biofilm, you can go and start a whole new colony of pond scum. So they are able to live independently if you remove them from their group. That's not necessarily true from an organism. If I remove, for example, some of your skin cells and I go and put them in a petri dish, I have to do a lot in order to keep them alive. If I take some pond scum and I go to another pond and I throw it in the water, if conditions are right, that pond scum, not only will it live, it will thrive and it'll eventually form a whole new layer of pond scum on its own. So a biofilm is not exactly the same as a multicellular organism. Instead, know that it's a group of unicellular organisms that organize themselves and they almost behave like a large multicellular organism. Almost, but not quite exactly. There's still a little bit of a difference. I know that this particular page is really detailed, so before I go on to pay the next example of a characteristic of living thing, would you type in a number 1 so that I know that you have copied everything on this page? Type in a number 1 for me into the chat window. Oh, good. You guys are keeping up well. All right. So moving on. Living things. This is number 4, I believe. This is page 4. So living things They all have to basically eat something. They all exhibit metabolism. Okay, they all exhibit metabolism. And metabolism is a word that describes all the chemical reactions that happen inside of an organism. Or I'll say inside of a living thing. All the chemical reactions that occur inside of a living thing. There's two broad categories of metabolic reactions. There's what we call catabolic reactions or catabolism. So catabolic reactions. And then there are anabolic reactions or anabolism. So metabolism is divided into these two categories. These are reactions that tear things apart, where anabolism are reactions that build. A good way to remember the difference is I think of the word catabolism as having, cat right there in the middle. So like the little organism, cats, and cats have claws. And what do they do with their little claws? They tear stuff apart. I like cats. I've had cats in the past, but I'm on a cat break right now in my life. I don't have a cat right now. I like them, but I think it's going to be a long time before I have another cat because my last cat was very traumatic to me and he tore everything up with his nasty little claws. So when I see the word catabolism, I think of my cat Smokey that loved to tear things apart. Another way that you can think about, what's the difference between catabolism and anabolism is we often hear the word steroids. And steroids are famous for adding bulk. And the type of steroids that build things or add bulk are called anabolic steroids. So if you need a little hint on how to remember the difference between anabolism and catabolism, you can think of the word anabolic steroids, or you can think of a little cat that likes to tear things apart. So all living things, they exhibit metabolism. They're going to have some chemical reactions that tear things apart, and they're going to have some chemical reactions that build things up. So an example of reactions that tear things apart, think about digestion. When you put food in your mouth and you start chewing, that is literally a catabolic action because chewing literally tears your food apart. And then as your food hits your stomach, it continues to be broken down chemically and also physically because your stomach kind of swishes the food around inside at the same time that it's mixing chemicals with it. But that digestive action is still tearing your food apart. When your food gets to the first part of your small intestines, we add more chemicals to continue the breakdown of your food. So digestion in general is a tearing apart or breaking down of whatever food or nutrients that you are using. Eventually, you're going to use those nutrients to build all of the body parts that you need. So for example, right now I don't have long hair. I used to have long hair, but I cut it not too long ago. My hair was a little bit down past my shoulders before I cut it. And so I'm thinking about growing my hair back to its original length. Well, growing the hair, whether it's the hair on my mustache, whether it's my new eyebrows, whether it's the hair on my arm, or whether it's the hair coming out of my head all the way down to my shoulders, the increasing in the amount of hair or the increasing of the length of the hair, that is a building reaction. And so where do I get the raw materials to actually build my hair? Well, from the food that I digested. So catabolism and anabolism, they work together in order to maintain literally our body parts. The whole reason that we have these is really to obtain energy. Metabolism in general, we do it in order to obtain energy from nutrients. Whatever you use as food. Now, we normally think of food as like being carbohydrates, proteins, and lipids, but there are some unusual bacteria out there that they can eat basically rocks, or they can eat gasoline, or they can even eat plastic. So, whatever you use as food, you're going to break it down and recycle the parts to get energy and to make new or replacement parts. One of the things that indicates that metabolism is occurring is the creation of a waste product. Or waste products. So breaking down stuff and recycling it is not 100% efficient. You always have some sort of a waste product left over. Oh, creates waste products. You always have some sort of a waste product left over. I'm curious. You can tell me out loud or you can type it in to the chat window. What do you think is the most common waste product in the universe? Think about it, and you can tell me out loud or type it in the chat window. What do you think is the most common waste product in the universe? Any ideas?
Food?
Food? Nope. Plastic? Nope. Somebody typed in plastic into the chat window. Nope. Try again. What do you think is the most common waste product in the universe? Paper? Nope. And when I say waste product, I'm talking about what are some wastes that we generate from like digestion? What are some wastes that we generate from, replacing our body parts? Christopher Woods, some sort of a gas. Oh, that's a good guess, Christopher, but no. I'll take one more guess. The most common waste product in the universe is heat. The most common waste product in the universe is heat. So when you break things down and you recycle the parts, you're going to have some stuff left over. And so you might have a little bit of organic waste left over. So if we're thinking of animals, of course, urine or fecal matter. But as many animals as there are in the universe, all the stuff that they produce, which we think of as being waste, it pales in comparison to the amount of heat that's generated. This is the most common form of waste in the universe. In fact, this is a good way that you can tell if something is undergoing metabolism, is look to see if that organism is generating heat. It's an indicator that metabolism is occurring? The generation of heat indicates that metabolism is occurring. So for example, your body temperature is approximately 98.6 degrees. That's an average. That's an average. Okay. So that is close to 37 degrees Celsius. So about 98.6 degrees Fahrenheit. Well, where do you think that body temperature comes from? A significant amount of your body temperature is coming from the waste from you doing these two things. And if you add that up to 10 people in a room, all undergoing metabolism, did you know that if you have 20 people in an average size room, their own body heat can raise the temperature of that room as much as 5 degrees? You know how I know that? Because I'm a teacher that spent time inside of a classroom in a typical high school. High school classrooms are not always very big, and we love to stuff bodies in those high school classrooms. And so if you've got a regular size classroom with 20 students in it, you can guarantee that the temperature of that room is going to rise as much as 5 degrees Celsius just from the body heat coming off of the students. So imagine that it's August or September and the students are coming back from PE or they're coming back from lunch where they've been sitting outside soaking in the sun. They're obtaining heat from the sun, but when they go back into their classroom, that's just excess heat that they're giving off as waste, in addition to whatever heat waste they're generating from digesting their lunch. Just some little teacher talk there for you guys. But that's true in any situation. This is why a lot of conference rooms are kept cold. It's to really kind of counteract the impact of packing in bodies into a relatively small space. Think about that next time you are driving in your car and you've got quite a few bodies in your car, especially in the summer in New Mexico. You can feel the heat being given off just by the bodies that are in the car with you. And hopefully, Christopher, that's the only thing you're feeling is just heat and not some sort of gas inside of your car. But I digress. I digress. Moving on. The next example of what living things can do is kind of supported by this idea of metabolism. Living things, they grow and they develop. Living things grow and develop. There's a little bit of difference between growth and development. When I talk about growth, I mean literally an increase in size. Okay? Living things get bigger. If we're talking about a multicellular organism, that means more cells. So for example, imagine a little baby versus somebody who is 15 years old. Obviously, the 15-year-old is going to be physically larger than the baby. So it makes sense that the 15-year-old is going to have more cells because he's larger as compared to somebody who's still a little baby. So in order to get physically larger, you're going to have more cells. Development is a little different. Development indicates a process of maturation. Maturation often happens over time. Sometimes a relatively short amount of time, sometimes a larger amount of time. But we'll take into example a tree. A tree that's still a seedling versus a tree that is mature. Mature trees have the ability to produce fruit. Okay. Let's say we're imagining a peach tree or a pear tree or an apple tree. Seedlings, those trees that are, still very small, maybe even a year old or less, they can't produce fruit. They may not even be able to produce leaves, much less produce a fruit. So there's something that happens in the development of a tree so that over time it is not only able to produce fruit, but it can produce leaves and it can heal itself. It can do all sorts of things that a seedling is not able to do. Sure, a tree that is mature is also going to be physically larger in size, but there's also going to be a period of development. In other words, a maturation that happens. So growth and development, they occur together. They occur together. Not only do living things get larger in size, but they gain abilities over the course of their lifetime to do things that they could not do at other stages of life. So you can think of this as like life stages. Growth and development is very tightly controlled. Very tightly controlled, most often by hormones. And these are special, what we're going to call signal molecules. A lot of things in our daily life are controlled by hormones. Even how we have our wake and our sleep cycles are controlled by hormones. But growth and development for any living thing is very tightly controlled by hormones. A good example is when you go to the store and think about fruit in the produce section. Like we'll say, for example, bananas and tomatoes. Well, when you go to the produce section of the store, a lot of times you'll see green bananas. That's because they are picked green so that they can mature along their travels from the fields to the store. So that's what allows maturation. Same thing for tomatoes. They are also picked green. But there's an interesting thing about consumers is that consumers know that green tomatoes are going to mature at their house in just a few days. And so consumers are willing to buy greener bananas. But tomatoes, consumers don't like to buy green tomatoes, usually. So what happens is that tomatoes are artificially matured. They are picked super green because green tomatoes are very firm and they travel better than tomatoes that are closer to ripening. But they are artificially matured by being exposed to a hormone called ethylene gas. Plants normally produce for themselves small amounts of ethylene gas, very small amounts. And that's what causes the ripening process for a lot of fruits. So both bananas and tomatoes use ethylene gas as a good ripening hormone. It just turns out that bananas seem to store their own ethylene gas better than what tomatoes do. Once you take a tomato off the vine, you're in a sense separating the tomato from the part of the plant that's producing ethylene gas. And so if you don't expose a tomato to ethylene gas, it won't necessarily ripen. It'll just stay green and it'll rot. And that's not what they want in the grocery store. So what tomatoes often do, or what growers often do, is they wait till a certain point in the shipping process and they literally gas their tomatoes. So they put them in a room and they fill the room with a little bit of ethylene gas. And in a couple of days, your very, very green tomato will turn red. But guess what doesn't happen? Is that there is no flavor development. Because all ethylene gas does for tomatoes is turn them from green to red, but it doesn't actually encourage the other chemical changes that occur inside of the tomato that brings on that tomato flavor. So if you've ever gotten a tasteless tomato from the grocery store, now you know why. Is they have been artificially matured by exposure to a hormone called ethylene gas. All that gas does, it caused them to artificially mature in one way by turning red, but the other half of the development doesn't occur, which is the flavor component. Isn't that crazy? Now, when you go to the grocery store, you can, be suspicious of your tomatoes. You're like, are you artificially matured? Yes or no? Just real quick, apples, by the way. Apples are kind of like tomatoes in that they're picked green and then they're exposed to ethylene gas. But these guys, they store ethylene gas in huge, huge, huge amounts. And then they give off the gas. And so for that reason, apples are often kept separate from everybody else in the produce section. So next time you go to the grocery store, notice how they separate the apples. Apples are never in the middle. They're always put at the edge, far away from everybody else. And you always keep them separate from the tomatoes, and you always keep them really, really far from the bananas. Bananas are also kept by themselves because they're unusually sensitive to ethylene gas. But if you want to artificially ripen tomatoes or bananas at home, just put some apples next to them. And the apples that you bring home from the grocery store, they'll continue giving off the hormone, the artificial hormone that they got, and it will cause your tomatoes and your bananas and everything else to ripen faster. I don't know if you've ever noticed that at your house, that if you put the bananas by the other fruit, everybody rots in like a day and a half. How come? Because the apples continue giving off the ethylene gas for a lot longer than all of the other produce. I've got time for one more thing. I put a lot on this page. Let me know if I can go on to my last page by typing a 1 in the chat window. I don't want to go too fast, give you plenty of time to write down the notes. Good, good. So number 6, living things, they use their metabolism to support what's called homeostasis. In the homeostasis, I can't point to it, but instead it's like a situation or it's an internal set of conditions that basically all of your systems have to adhere to. And I'm going to say it this way, that constitute what we think of as your health. Oops, I misspelled health. H-E-L-T-H. There we go. It's an internal set of conditions that kind of constitute your health. So if I was to ask you, are you feeling, healthy right now? What is it about you that indicates that you're healthy? How do you know you're not sick? Well, you might say something like, well, Mrs. Weir, I don't have a fever because my body temperature is about, again, 37 degrees Celsius, or it's around 98.6. I'm not hungry because my blood sugar levels are good. You know, my blood sugar level is about 90, and that would be milligrams per deciliter. My heart rate is good. I don't have a racing heart. So my heart rate is somewhere around, we'll say, 80 beats per minute. My blood pressure is good. My blood pressure is about 120 over 80. These are examples of things that make up your homeostasis. These are internal conditions that kind of constitute your overall health. So your body temperature, your blood sugar levels, your heart rate, your blood pressure, whether or not you're dehydrated. There's lots of little things that constitute your homeostasis. Your body works very, very hard to maintain these levels. It's possible to be hotter or colder than 37 degrees. It's possible for your blood sugar level to be higher or lower. And the same thing for your heart rate and your blood pressure rate. These things can still vary and you remain healthy. In other words, they can go up and down without severe distress. But what would happen if your body temperature went from 98 to 104? Is that considered a good indicator of health? Of course not. We would say somebody who had a temperature of 104.1, they probably feel terrible. They have a really high fever. In other words, this is stretching the limits of your homeostasis. It's indicating that there is something compromising your overall health. If your blood sugar level all of a sudden went to, let's say, 300, that's terrible. That's terrible. That is way outside of the range that we would consider to be healthy. Or if your heart rate skyrocketed to 200 beats per minute, that's awful. Or what if your blood sugar, or blood pressure, your blood pressure dropped to 60 over 20? Oh, that's way outside of an acceptable range. So the idea is that you can go outside the range of your homeostasis, but you will suffer. You're going to suffer. And so your body works to correct it. Your immune system is going to figure out what is wrong that is causing such an extreme change in my homeostasis. It's possible to recover, but sometimes if you stay out of your homeostasis for too extreme for too long, sometimes your recovery is limited. So sometimes you're okay, but sometimes you suffer damage. So, for example, if you have a temperature of 104 for an hour or two, you're going to feel really bad, but chances are you can recover if your body temperature reverts to something more normal. But if you were to stay at 104 for several hours, maybe even a whole day with no break, or if you went to 104, 105, 106, you're going to suffer some damage. And it's possible that you don't recover at all. Sometimes being too far outside of your homeostatic conditions for too long there is no recovery. So as such, we know that all organisms, all cells, all organisms, their systems, cellular, they spend most of their energy maintaining their homeostasis. It's that important. It's that important. Living things spend most of their time maintaining their homeostasis. I'm going to stop here for today. I have one more thing to add to this list, but I don't have enough time to discuss it. So I'm going to stop here for today. Next time, we'll finish this list and we'll pick up the last item, and that is reproduction, or last items, which is reproduction and evolution. So we got two things to add to this list: reproduction and evolution. Oops, there you go. Reproduction and evolution. And I just want to remind you, especially if you joined us a little bit late, okay, I just want to remind you that right now in the week 2 folder, there is the chapter 0 quiz, which is on the scientific method. I misspelled it. Then there's the chapter 1 quiz, which is going to be over what I call the intro to biology. We'll finish the intro to biology on Wednesday. And then there's the chapter 0 and 1 question. And you'll see the link to the flip grid. So just as a reminder, what assignments are due: the chapter 0, chapter 1, and the chapter 0 and 1 question. These are each worth 100 points. And they are all due on the same day, which is 1 week from today, Monday, January 25th at 11:59 p.m. And you can find them all again in the week 2 folder. I'm going to stop the video or the recording